Hello, I'm Sam Knight, hailing from Sandia National Laboratories. My talk is called Using Malleable Task Scheduling to Accelerate Package Management Installations. I think the name got changed somewhere in between. I manage a cluster, and I was building hundreds of packages and deploying a software stack using the Spack package manager. And I was discovering that the build node that I was using was getting poorly utilized. And excuse me. And if you look at the plot on the bottom there, you'll see that the speed up time. So this is taking the one core execution time for an installation, and then normalizing that, and then seeing the maximum speed up time you'll observe on a node. And this is on a 32 core node. The execution times were very poor. The best speed up times were very poor. This particular plot makes it a little bit worse than it was, because a lot of the larger packages would tend to scale a little bit better, and a lot of the smaller packages tended to scale worse. So if you were to build all of these, you wouldn't see such a drastically poor execution time. And this is significant because just ignoring my use case where I was building hundreds of packages, but in a use case where you're even just building a few dozen packages, scientific libraries can take a very long time to build, hours, sometimes days. And so looking more into this behavior, there are a couple of reasons I could find why a particular build system would scale poorly. First of all, most build systems are going to have a long serial step, like a configure step. CMake has something similar. And this is, in AutoTools case at least, the configure script will run a bunch of program stubs to sanity check the environment, to check how big an int is, behaviors like that. And that will never scale. That'll always at best peg one core. And in addition to that, the part that you'd always expect to speed up, a make file, that doesn't always speed up as well as we would hope. There's a couple of reasons for that. So a make file is going to traverse through a directory tree, and at the end of a batch of builds, it's going to do a serial linking step, and that's going to not scale. And in addition to that, as the number of jobs in a particular directory, or as the number of objects to build in a given directory decrease, you're going to temporarily run into a state where the job queue is starved. So moving on to how, just a little bit of information about how Spack works. So Spack will install a package from source, and you give Spack a spec, and that's just an abstract specification for what you want to install. So let's say you want to install OpenMPI, and then Spack will trace out a tree of dependencies, and then a concretizer will filter through and fill in all of the missing details, and then that results in a completely concretized build tree. And then when Spack tries to install a package, it's going to traverse that tree all the way to a leaf, and a leaf is just a package who either has no dependencies or all of its dependencies are already installed, and then it will build that. So in this example, if we want to build Perl, it's going to depend on GDBM, which depends on readline, which depends on ncurses, which depends on package conf, and then Spack will reverse the traversal and work all the way back up to a Perl installation. And then when Spack installs a specific package, it's actually going to execute a pipeline of phases. And so, for example, an AutoTools package it comes with this set of 4 phases that it'll iterate through, and at the end you should have an installed package. And then where possible, Stack will try and fan out and exploit the parallelism on a given node. If you have, say, 8 cores and they're hyper-threaded, it'll fan out to 16 and hopefully improve the build times. In this case, it would speed up the build and install step. Configure and autoconf obviously would never speed up. So moving along, we have to introduce this idea of a malleable task. If you imagine a task as being some abstract piece of execution, a malleable task would be one in which you could change that execution time by varying the allotted resources. In this application, that would be the number of cores. And a build system, more specifically the make step, would be an example of a malleable task. And so the central insight here would be that if we know that build systems don't scale perfectly, and in fact in some cases scale very poorly, well, instead of the default behavior where we just fan out onto all of the cores, what if we were to give a smaller allotment of cores to a given build system, and that would allow us to have inter-task parallelism with multiple build systems. And the execution times for a given build system might be a little longer, but overall our execution time will decrease a little bit. And we'll discover shortly that there are cases where this can actually give us a pretty substantial improvement in execution time. So moving on to task scheduling, there are a couple of concepts here that we have to introduce. These are, and I'm going to go through them pretty quickly, but these are features of a task that the scheduler is going to use to compare tasks or to prioritize their builds. One is top level, so that's the longest path from the current task to an entrance task, excluding the task start time, or sorry, the task execution time. So if you look at the top row there, in this sort of simplified dependency tree for OpenMPI, the top level is always 0 for an entrance task because there's a 0 length from it to an entrance, and then all the way down at MPI, it's maximized. And then bottom level is the reverse direction, so the longest path from an exit task, but this also includes the execution time. And then we include the execution time so that we can introduce this concept called a critical path. That's the longest path through a given task. And the consequence is that when you add the top level and the bottom level for a given task, you'll have the critical, let's see, sorry, in the critical path, in this example, the critical path is maximized along the build tree where libibconf, XML2, HWLock, and OpenMPI trace. And this is important because this gives you a lower bound on the minimum execution time for a given schedule, right? This is a serial chain of tasks that you can't improve on for a given schedule. Oops. Sorry about that. And then we need to model our malleable task execution times. And so I got the chance to cite the most cited paper ever, Amdahl's law. And the idea of Amdahl's law is that executions have two parts. There's a part that you can optimally improve execution time by running in with parallel across multiple processes. And there's also the serial component. So abstractly using this, if we have a malleable task and we assume that the task has a component that doesn't scale, and since the serial component and that sort of one core execution time of task is independent of the number of cores we allot, then we could simplify this to be a constant divided by another processes plus another constant. And then we can determine what these constants are by taking samples of different execution time or different executions with different core counts of a given task. And the result is the result gives you a curve that you can approximate with the linear approximation. And I was able to do that with least squares. So I used two-step schedulers for this implementation. One is called critical path reduction, or CPR. The other is called MCPA, modified critical path allocation. And I picked these two because so these are both approximations, right? Doing this is actually an NP-hard problem. And so I picked two that have two different time complexities. So the CPR algorithm has higher time complexity, and then MCPA has lower time complexity. The first step constitutes creating a core allotment for your tasks, and then the second step consists of actually building the schedule. Both of them are going to use the same algorithm, the Tasklist scheduling algorithm. I'm kind of skip over the slide, but effectively this just shows you the components driving the time complexity. So there'd be the number of dependencies, the number of tasks, the number of processes, and then MCPA is going to have this idea of precedence levels. So if you were to take horizontal slices of your tree, each slice would be would have tasks that are independent of each other, and it's not present in CPR, but it does drive time complexity in MCPA. I'll describe the CPR algorithm because it's the simplest. I do have a paper on this, so if you want to see how the others are implemented, you should look at that. But every task initially starts with one processor allotted to it, and then an initial schedule is created, and then the outer loop is entered. The outer loop will repeatedly call the inner loop until the inner loop can't improve the schedule. The inner loop is going to try to add a core to one of the tasks, and it will prioritize one that's more critical. And then if it's successful, it exits in the outer loop and repeats, or if it's not successful, it'll remove that process and try another task until it runs out of tasks. So I did a couple of changes. As I was implementing the reference schedulers, I saw things that I thought I could improve. One was FCPR. So FCPR is very time consuming to run. So let's say, what if we were to filter out some of the tasks? Let's say these don't really scale that well. We'll just remove them and then hopefully improve the time without hurting the quality of the schedules too much. And then I also wrote a variant of MLS. So when we up here we saw that that MLS gets called a lot because it's going to generate a schedule every time it's in that inner loop. And so if we and since we're only changing one core and one task every time, that means a big part of the schedule is it doesn't change, and so we can just memorize that part of the schedule, and that should improve execution time. And then there's hole filling, so just picking the processors with the earliest start time could cause holes in the schedule. And so if you pick later processors that don't increase the start time for even task, and then potentially you could prevent holes from forming in your schedule or decrease the occurrence of holes forming in the schedule. So I benchmarked on two systems. We'll call them Node A and Node B. And the real difference here are the file systems. Node A would be what you see on like a workstation, just a SATA SSD. And then Node B had a local NVMe memory, but it also had NFS for parts of its file system. These are packages that I benchmarked on. I did this mid last year, and I guess some of these are already out of date, like Python 2 and XSDK 4 or 0.4. But what we really care about are the size of the package counts. That'll drive the complexity of these algorithms, and it also sort of show us the behavior as we look at different numbers of packages and how they interact with the number of processors available. So first, it's schedule creation time. This doesn't deal with schedule execution time. This is how long it took the algorithms to create a schedule. And we can clearly see that MCPA was the fastest. FCPR, in all but one of the cases, the exception of TK, was able to also generate a schedule faster, and CPR was the slowest by a good margin. This is on a logarithmic scale, so these aren't you aren't intended to try and get an exponent out of this, but we can see, since it's on a logarithmic scale and there's a different slope, that we would indicate that yes, in fact, that we can empirically see there's a different time complexity. And we can also see with the CPR that the increase of packages is causing is quite heavily driving the increase in execution time. In this case, 2.5 seconds for XSDK, that's still in the noise. So at that scale, at the scale tested here, we don't really have a problem yet. But if we were to maybe double it a few more times, then we probably would want to use a different scheduler. So FCPR, this algorithm did have a much better schedule execution time. You can see in the best case it was about 42% with the MLS, and then CPR had a similar schedule creation improvement time with modified MLS. And so this is the brass tacks here. So there are 2 columns. Those are for the 2 respective nodes, and then the top row are the estimated schedule execution times. So this is where the scheduler creates a schedule and then looks at its own schedule to see, okay, how much more quickly do I think this will run? And this gives us a basis for asserting that the schedule actually has a estimation, or the malleable task heuristic we used, rather, it has an estimation that's grounded in reality. And on the bottom row, we can see the improvement in execution time. The colors are for each algorithm, and then the red one would be if we just ran it sequential make jobs that fan across the entire node. So that would be the Spack's default behavior. And the first thing we see is that in cases where we have looks like larger packages or larger package counts do seem to perform a little bit better, had the best improvement, so better than doubling its execution time. XSDK also improved quite a bit. I think the behavior point out here, in my intuition, tells me that when you have smaller package counts, like in the case of Python, you won't see as great a speed up, and also in cases where you have a lot less cores, because then you won't see the loss in scaling that would otherwise occur when you have much wider systems. We also can see that MCPA performed pretty well. It compared to CPR, despite having a much lower time complexity. And then we can also see that that the estimations for the execution time, I guess more specifically the speed up, are roughly on par. We do see a little bit of drift for some of them, but in general, this heuristic worked pretty well. And then we do see some instability from FCPR. So the filtering, when applied too aggressively, or in some cases, doesn't work very well, and it results in worse schedules. And then one thing you might ask is, okay, well, what about disk? Why this model doesn't account for disk? Wouldn't that hurt the behavior or hurt the performance of the heuristic? And I would say maybe if it was 10 years ago, if we were using a hard drive, yes, that's possible. We do have to note, though, and I wasn't using particularly new SSDs. So Node A was a SATA 3 SSD. Node B did have NVMe, but it was running. It was a circa 2015 NVMe. What we have to note, though, is that SSDs they're much faster in terms of transfer speed. What they really win over hard drives is their IOPS. So random accesses are going to perform much better, easily 3 orders of magnitude better than a hard drive. And so that didn't seem to affect these results that much. So there are things that are in the works for the future. Eventually, I'm going to have these changes put in upstream Spack, so the world can use them. There's some question about how portable using samples from one system are on another one. Our thoughts are perhaps if Spack just has some notion of an X11 header is going to install much more quickly and much less scalably than OpenBLOS, then maybe it really doesn't matter that the heuristics are off by a little bit. But there are a number of other things that could be improved. So I used a package task. So an entire package is your malleable task. However, if we were to decompose them into phase tasks, where the dependency tree is the same, however, each task is broken into a serial chain of phases, maybe that would improve it. I didn't have the chance for this work to really try that, but I think that would be potentially, if you have enough parallelism, that would be a good place to try and find more improvements. I did not attempt hyper-threading or over-provisioning, but that could potentially also cause improvements, because that would maybe squeeze out some more gaps. I didn't assess that the system was completely pegged even when I used this method. And that's about it. So yeah, in conclusion, a lot of time is spent building software. I spend a lot of time doing it. I know a lot of other people spend a lot of time doing it. It's something that could be improved. And I was able to demonstrate with some small changes in Spack how you could implement a scheduler that could structure a build system, a series of build systems in such a way to improve their execution time. And in every case at my scale, which consisted of single package or single top-level package DAGs, I was able to use every one of these schedulers to improve the build times, and with a insignificant schedule creation time. And I do have a branch. I don't recommend you use it though, because I'm going to upstream this soon, and that branch is like a circa April fork of Spack. So if you really want to look at it, it's there. That's all.